In this video, we're going to start moving into rational numbers. So let's first of all define a rational number. A rational number is the quotient of two integers. So for instance, if we have a rational number, and remember Q is the way that we define a rational set, R is rational if it can be written in the form A over B, all right, so quotient of two integers, and A and B share no common factors, right? So for instance, the number 2/3 is clearly a rational number, right? However, pi is not a rational number because we can't write it as a quotient of two integers, all right? Some people use 22/7, but remember 22/7 is just a decent approximation in terms of the rational number, but it doesn't really give us a good representation of it, okay? So let's do just a couple examples in which we can show a number is rational. Now, we're not going to show that a number is not rational yet. We have to learn another technique later of contradiction or contraposition. But for now, we're just going to go through and use the definition of rational. So an easy one, right? 37 is rational. Well, 37 is equal to 37 over 1. So any whole number is rational, right? And notice that this could be defined as A, which is 37, B, which is 1, all right? And so it fits the form A over B, and there's no common factors other than 1. All right, so that's a pretty easy one. A trick that you might have seen is to show that a repeating number is rational. All right, so we have 0.83838383, dot, 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 all right? And we want to show that that's rational. Right? Let's assign that to the value x. Right? So I'm just going to go ahead and define this as x, right? And what we could do is we notice that every 2 decimal places, the number repeats. So we could multiply by 10 square, or in this case, 100. So we know that 83.83838383 da 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 is equal to 100x. Now we don't want to use 1000x because that would be the 838838. So what does that mean to us? Well, we know that if we were to subtract these, we could go ahead and say that 100x minus x, and we know that 100x is just this 83.838383, da da da. And we know that x is 0.838383, da da da. And we're subtracting these. So what happens? We get 99x is equal to 83. Right? And now we can say that x is going to be equal to 83 over 99, which is rational, right? That's the very definition of a rational number. And so we can say that since 0.838383 da 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 is equal to 83 over 99, hence it is rational. It's of the form A over B, okay, where A and B are integers. And I should say A and B are elements of the integers, just to be technical about it, okay? So just a couple ways that we can go ahead and show numbers are rational. And again, we're not going to disprove rational at this point, right? Because we need a little bit more powerful technique than direct proof. Let's take a look at one example of being able to utilize rational numbers. And we're going to say that for all x, y, and z that are rational, that means that 2x squared minus y plus 2z is also rational. Same steps. Let's let x, y, z be elements of Q, okay? And we're going to say x, y, z are arbitrary but particular. All right. We know that there's a definition for rational numbers, all right? So these aren't integers. Remember, a rational number is written of the form A over B, all right? So we can say by definition of rational, Right? So we're going to have a lot of definitions going on here. We're going to say that x is equal to, let's just say a over b. Let's say y is equal to c over d. Right? And we're not going to reuse a and b because that would mean that x and y are equal, and we certainly don't want to imply that. And then we're going to say that z is going to be equal to e over f. Now we have to make some definitions for a, b, c, d, e, f. Okay, so we're going to say a, b, c, d, e, f are all integers. We should probably state that b, d, and f are non-zero, just because they're in the denominator. And furthermore, we should probably say that a and b share no common factors, c and d share no common factors, and e and f share no common factors. All right, so we're going to say a, b share no common factors. We're going to say that C, D, and I'm just going to use quotation marks because share no common factors. And then finally, E and F share no common factors. All right, so a lot of stuff that we had to do just to be able to do the definition for this. Right? Next thing, we're going to go ahead and verify the conclusion. 2x squared minus y plus 2z is a rational number. Okay, so substitution. So by substitution, we say that 2x squared plus y minus 2z, or sorry, minus y plus 2z is going to be equal to 2 quantity a over b squared, right? Because remember, x is a over b, minus c over d, okay? And then finally, e over f. So plus 2 e over f. All right, now, what are we ultimately looking for? We're trying to show that somehow all of that is rational. And remember, a rational number is quotient of integers. So we have int 1 over int 2. All right, so that's what we're looking for. So here's how we're going to do that. First of all, let's use just some exponent rules and some multiplication, and we can rewrite this statement on the right-hand side as 2a squared over b minus c over d plus 2e over f. And we can say that's just by multiplication and exponent rules. Technically, it is just multiplication. Okay, so we could say multiplication, exponent rules. We want to get a single integer. So to be able to get a single integer, we probably need a common denominator. So let's rewrite everything with a common denominator. Right? Now, the common denominator for this one is going to be BDF. So we have BDF. So we're going to rewrite everything with the denominator BDF. And we still have 2a squared up top. And we still have c up top. And we still have 2e up top. Okay? And what we have to do is we have to find out what we're missing, and we have to multiply that in the numerator. Right? So look at this first fraction. We have a b and we have a b, but we're missing df. So that means in the numerator, we have to multiply that by df to compensate. Right? So it's just like if you were trying to turn 2/3 into 4/6, you have to multiply the top by 2 because you multiply the bottom by 2. Right? Same thing here. We have a d. So that means to go from the second fraction's denominator to the new denominator, we need a bf. And then finally, we have f, so we need bd in the numerator to compensate. Right? So just a quick review of how to do some of these algebraic fractions. Okay. So what does that mean? Okay, and by the way, this is by common denominator. Well, that means that now we can combine this into one big old fraction, and now we can rewrite this with a single denominator of BDF, and we have 2a squared df minus cbf plus 2ebd. Right? And we could just say that's just by addition. Okay. So I'll just say, I'll try to squeeze that in here. And what do we have in the numerator? Integer times integer, integer square, integer, integer. So this whole thing's an integer. CBF is an integer. 2EBD is an integer. Integer minus integer plus integer is an integer. All right, so let's just call all of that, we're running out of variables, but let's just call it M. Okay. And then the denominator, let's call that N, right? And that's just by integer closure. All right, now we have to make sure that we define M and N. Okay, so we're going to say that M, comma N are integers. N is non-zero. Right? And then also, if you really wanted to, we could say M is equal to 2a square df minus cbf plus 2ebd, and N, mercifully, is bdf, an easier one. Okay. Now, what have we shown? We've shown that 2x squared y 2z, or minus y plus 2z, is equal to m over n. Okay, so thus 2x squared minus y plus 2z is equal to m over n, which is rational. By definition of rational. All right, and so what does this mean? It means we're done. So hence, for all x, y, z in rational, that means that 2x squared minus y plus 2z is also in rational. All right, and I would probably sneak something in right here that I probably should have before. We could say thus by above. All right, so, but it's clearly obvious in the previous step, it's self-contained. All right, but if we wanted to be totally explicit about it, we would just write the by above. All right, so in our next video, we're going to take a look at one more example of rational, and then we're going to move on to our last concept in this section, which is going to be divisibility.